Hello, welcome to the fifth lecture of the course. So today our focus is going to be sorting algorithms. In particular, we will be looking at lower bound for comparison based sorting. So let's just begin with the problem definition once again. So in the last lecture, towards the end of the last lecture, I just briefly discussed the problem, but again we'll go over it. So here our input is an array consisting of n integers. Okay, so you can assume non-negative integers if you need, but it doesn't matter. Okay, so you can have negative integers too. The output is elements of A in sorted order. So what is the sorted order? It could be ascending or descending. So for now, for the purpose of this lecture, let's assume that it's ascending. Okay, we can modify the algorithms or lower bounds accordingly, even in the case of descending order. Okay. So yeah, when we talk of sorting algorithms, we need to talk about models. Okay, so what is it we can assume, what is allowed. Okay, so here we are saying that the array consists of arbitrary integers. Okay, there is no bound on the integers. There is the value could be anything. So we cannot say that okay, elements will be from 1 to n or whatever. It's unbounded. Okay, it's not from a fixed domain. So the assumption is we can compare any two elements in the array with unit cost, or we can compare an element in the array with some number, absolute number that your program has, with unit cost. Okay, so the cost of comparison is considered as unit. Okay, so again, so here to compare to n bit integers or some m bit integers, you will require time proportional to m. Okay, but we are taking it as unit cost, and we cannot assume anything about the actual values. So the cost measure is simply the number of comparisons being made. Okay, so now you might be wondering, why do you need such a restriction and so on? Well, you can have algorithms which does not make this assumption. Okay, so this just simplifies the process, simplifies our understanding. So at least we will be able to understand what is the minimum number of comparisons required. And you can see that this is kind of necessary if you assume nothing of the domain of values. If the values are unbounded, this is the best possible, because there are sorting algorithms which use the domain knowledge like radix sort and so on, which depend on the values being bounded by some number or whatever. Only then they will work. Okay, they will work fast. Otherwise, they are not better than comparison based algorithms. So yeah, so we have lots of examples. I am not going into the details of any of it. You might have seen this in your first algorithms course. So bubble sort, selection sort, insertion sort, etc. You might also done analysis saying that the number of comparisons required is order of n square. Okay, so there could be best case instances where the number of comparisons could be order of n, but there are always worst case instances where the number of comparisons is at least n square. Okay, up to a constant factor. And then there are algorithms merge sort and heap sort, which will require n log n comparisons. Yeah, which does sorting in n log n comparisons. Then again, quick sort, you might have heard that it's n log n on average, but n square in the worst case. We will come to it soon towards the end of the lecture. So just to to be precise, so I'll just put the comparison model here. So any comparison operation is counted as unit time operation. No assumption on the inputs except that they are integers, and we will not count any other operation. Okay, so you can ask, okay, why? I mean, moving an array element or swapping elements and so on. Yes, we can count them. Typically what happens is, for a comparison operation you will not be doing unbounded number of such operations, you will be only doing bounded number of operations. So asymptotically up to constant factor our analysis will be good enough in such cases. Okay, it is possible that you have an algorithm for every comparison, it does some n move operation and so on, but then if the number of comparisons, say if I prove a lower bound of say n log n to the number of comparisons, such sorting algorithm is going to be useless, right? Then you require n square times log n time. Okay, so typically we can expect the number of other operations proportional to the number of comparisons. Okay. So the lower bound question is the following. So what is the minimum number of comparisons required to sort an n element array? Okay. So you can easily see that n comparisons are needed, say in fact n minus 1 comparisons are needed even to read the input. Okay. So yeah, I'll leave it to you to argue it out that at least n comparisons are needed. I'll skip that part. And using merge sort or heap sort, you know that order n log n comparisons are enough. Now the question is, can we argue that at least up to a constant factor n log n comparisons are required? Okay, so when I say omega n log n, so this is a lower bound. So can we prove that any sorting algorithm will require omega of n log n comparisons? And answer is yes, and that is what we are going to do today. Okay, so this is the formal statement. So again, for today's lecture and for this statement, notes is Avram Blum, I think third in the sequence. Okay. So let me just read out the formal statement. So any comparison based sorting algorithm must perform omega n log n comparisons to sort an array of n elements in the worst case. So this is very important, in the worst case. Okay. So in other words, equivalently, so for any deterministic, so you can ignore the word deterministic, I mean any usual algorithm that in our sense an algorithm, comparison based sorting algorithm, let's call it as A. So for all values, so n equal to 1 is fairly trivial, so n greater than or equal to 2, there exists an input array B of size n such that, so there is an input array B such that algorithm A, so this should not be B, so A makes at least log of n factorial, which we can see that it's up to a constant factor, it is n log n comparisons to sort B. Okay, so this is the lower bound. It says for any algorithm, okay, and for any value of n significantly large, so here n greater than or equal to 2 should be enough, I think. There is at least one array where your algorithm will have to make omega of n log n comparisons. This does not mean that for every n, for every array, your algorithm will make n log n comparison. No, there could be instances where your algorithm requires only order n comparisons. This only guarantees just one array. Okay, so yeah, in fact there could be more than one arrays, but it just guarantees one array. So this is the worst case model So in the worst case model, for example, when you say upper bound holds for all inputs, okay. When I say lower bound in the worst case model, lower bound holds for at least one input. That's how it is, okay. So it could be that you have a comparison based sorting algorithm which performs only order and operations for almost all input except just one array. So this algorithm might be practically very useful because that one array may not come up in practical scenarios at all, okay. Whereas theoretically for us the algorithm will still require omega n log n comparison. So this is the worst case scenario. Okay. So we are going to revise a bit of basics. I mean, we'll need a permutation view of sorting algorithms. So let me just briefly introduce permutations. Okay. So suppose we have n elements. Okay, I'll change the color. Okay. So say 1, 2, 3, 4, etc. n. Okay. So we'll have running examples. So a permutation of 1 to n is an ordering. The elements. So for example 2, 3, 1, 4, 5, etc. up to n. So example, let's take n as 4. Okay. So permutation 1 is 2, 1, 3, 4. Another permutations 1, 2, 3, 4. 1, 3, 2, 4. 4, 1, 3, 2. 4, 2, 3, 1 and so on. Okay. So there are lots of permutations. So total number of permutations so you know what it is, right? So there are n positions. You choose the first position, there are n values, and then for the second position there are n minus 1 values because one value is already chosen, and so on to 1. So you know that this is n factorial. Okay. So here 4 factorial permutations. What is 4 factorial? 4 into 3, that is 12, into 2, 24, right? So there are 24 permutations on 4 symbols. So there are n factorial permutations here. Okay. Yeah. So you can imagine. So see, the point is, for permutations, it really does not matter how do I label these elements. Okay. If I write it as 1 to n or a1 to an, where a1 to an are the array elements and so on. Only thing is, I want the elements to be distinct. Okay. So we'll be assuming that the array has distinct elements. Okay. This is only for the purpose of lower bounds. Your algorithm will work when array has repeated elements, but for lower bound we will be displaying worst case inputs which have distinct elements. Okay. Yeah. So just to recollect, when I say a permutation, it is just an ordering of the elements. So for simplicity, I'll just label the elements as 1 to n. The actual elements could be different. Okay, since they are distinct, I can just label them arbitrarily. Okay, I mean one need not be the smallest value and so on. Some ordering. Okay. So now we are going to take a view which basically tells that Any sorting algorithm, what it essentially does is applying a permutation. Okay. So let's take this as input. So the input is a 6 element array 14, 16, 8, 3, 1, 6. Now what is a sorted array? 1 comes first, then 3, then 6, then 8, then 14, then 16. Okay. So I can view this transformation as an application of permutation. Okay. So I'll write the permutation as 5, 4, 6, 3, 1, 2. So what does it mean? So this says 5 occurs first. So where is 5? So there is no 5 in the array, right? So for that, what we do is we just label these elements as 1, 2, etc. up to n. So I label this as element 1, element 2, element 3, element 4, element 5, element 6. So it just says value occurring at position 1, value occurring at position 2, etc. etc. These are not values 1, 2, etc. The actual values are written there. Okay. So now this says, when I say 5 here, so the first element of the sorted array should be the fifth element in the actual array, okay, which is 1. The second element in the sorted array should be the fourth element in the actual array, which is 3. Okay. The third element in the sorted array must be the sixth element in the actual array, which happens to be 6. Okay, which need not be 6. In this case, the value happens to be 6. And the fourth element should be third element in the actual array, which happens to be 8. The fifth element should be the first element in the actual array, which happens to be 14th. Okay. So I hope it is clear. So this way, irrespective of the input array, so only thing that you need is, so for this sorted, so this permutation view, we'll need the elements to be distinct. If they are not distinct, say if I have 6 occurring twice, then you will not be able to distinguish. But even then, I mean, you can view it as a permutation. There's no issue. Okay. But it helps if the elements are distinct. That's all. It's not necessary. See, if I had, instead of 6, if I had 3 again, right? So the same permutation holds, there is no issue. Well, there is also another permutation, so the permutation may not be unique, that's the point, okay, because you can permute. So if I had 3 here instead, okay, so let's say, so let's take that example, okay, just to understand. Say 14, 16, 8, 3, 1, 3. Okay. So let's write down the sorted permutation. So first least element is position 5. So permutation, I am only writing the permutation for now. So first element should be 1, which is position 5. So let's mark the positions also so that it's easy to read. So position 5, and then position 4, and then position 6, and then position 3, position 1, position 2. But there is also one more permutation, right, which is position 5, position 6, position 4, position 3, position 4, position 3, 1, 2. So both are valid. Okay. So the only difficulty in considering repeated inputs is you may not have a unique permutation. Okay. So that's the only problem. Yeah, that kind of hurts our analysis too. So, but then you might be thinking, okay, so then I'll be losing that. No. So the point is, go back to the statement. So The statement here says for any algorithm there is an array, arrays of our choice. Okay, so we can always insist that arrays have distinct elements, because sorting algorithm will have to deal with that case too, right? Sorting algorithm cannot assume that elements always repeat. It should also work for elements, for cases where elements repeat or values repeat. Okay, so that is all. So that's, this assumption really does not do any harm, it only simplifies the process. So yeah, so the viewpoint that we are going to take is the following. So we'll view output of a sorting algorithm as just simply a permutation. So instead of this sorted array, it's equivalent to consider this permutation. See, once you know this permutation, you know what is the sorted array, right? So it's equivalent, and once you know the sorted array, of course you know what is once you know the sorted array, you know what is a permutation. So they are kind of equivalent. So if the elements are distinct, then the permutation is also unique, it is fixed. Yeah, so yeah, so for a given input, such a permutation is unique, subject to the condition that elements do not repeat. So I'll just write it here for clarity. So provided elements do not repeat. Okay. Yeah. So yeah, just to recollect, so given an array of n distinct elements, there are certainly n factorial unique permutations. So our algorithmic output could be any of these permutations. Okay. So this is the points to keep in mind. Now we are ready to prove lower bound. Okay. So before proving the lower bound, let's just try to understand. Okay, so let's just try to understand sorting algorithm with this viewpoint. So you can view a sorting algorithm. So a sorting algorithm so it performs a sequence of comparisons or series of comparisons. It might modify the array or whatever, and we'll imagine that can do some operations, any permissible operation. It can add, multiply if it want, I mean it does not matter, we don't really care, such as moving array elements, any other operation, any other okay, and then outputs a permutation. So instead of sorted array, we'll output the permutation. We'll just imagine that it outputs a permutation. I hope it is clear, because once you know the permutation, you know what is the sorted array. Okay, so it's straightforward to get the sorted array. So all we need to know is the permutation. So this is the view that we are going to take. Any sorting algorithm, it performs a series of comparisons, okay, and then outputs a permutation. Now the question is, okay, does it really matter, or doesn't it matter what operations it performs? We don't really care. So what is the intermediate array? We don't really care. Does it use an additional array? It does not matter. Okay, so we are only bothered about comparisons performed. Okay, so now the important point, so a important viewpoint that actually helps us. Okay, so we are going to view the algorithm as a tree. Okay, so a decision tree view. Okay, so let's imagine, so this is the start. Okay, so the nodes in our tree are going to be comparison operations. So this is the first comparison. Okay, so upon the first comparison, so any comparison operation will have two outcomes, right? So outcome 1, outcome 2. So let's say greater than, less than or equal to. I'm just writing, I mean the comparison may not be less than or greater than, it might be equal to whatever. Okay, so I mean these are the only comparisons, right? Because when I say sorting algorithms, elements should be from an ordered set, right? In fact a total order. So the corresponding comparison, in our case we assumed it to be integer, so that's a natural less than or equal to comparison. Okay, so these are the two outcomes. Then the algorithm goes into two new states, possible new states. It will in fact go into exactly one of these depending on the input. Okay, so input A. Then again for each of these, so it will do second comparison. See, remember that the algorithm will be in one of these, okay, it won't be both. So for us, the pictorial view is we are just getting all possibilities. Okay, and then third comparison for each of these. Etc. At some point it will end. Yeah, so here this last comparison. These are the outputs. Okay, so what is an output? Output is a permutation. Okay, so just to be precise, so let's denote Sn be the set of all permutations. Of an n element array. Okay, now I know that cardinality of Sn is n factorial. Okay, so here output is, we just label an element in Sn, sigma 1, sigma 2 in Sn and so on, some sigma r. Okay, so let's just see things again. So you have an input. Okay, so the algorithm essentially can be drawn as this tree. Well, now there's a confusion, right? What I have is a program, now I am drawing a tree. Come on, how tree can be an algorithm, right? So what I did is, I didn't write down the algorithm. See, algorithm is some supposed algorithm, okay? An adversary is giving me the algorithm, okay? I have to argue against every algorithm. So that means algorithm is arbitrary. What I did is, I just drew a tree which represents the comparison relations in the algorithm. Okay, so this only represents a sequence of comparisons. Okay, so this only says, okay, after the first comparison the algorithm has two choices. If the outcome of the comparison was say greater than, then it will do a second comparison, then again which leads to two choices, say like greater than and less than or equal to, greater than and less than or equal to, and so on. Okay, so this is only drawing the possibilities for the algorithm, and any other work done in between, after between the first comparison and the second comparison, we completely ignored it. Okay, so there is some computation that is happening here, there is some computation that is happening here, there could be a for loop or whatever, we don't really care. Okay, we are only interested in what comparison the algorithm does, and outcome, we are modeling the outcome of that. So we are saying, okay, outcome was greater than, then we'll go here. If outcome is less than or equal to, we'll go here. So these are basically states of your program. Okay. So now let's analyze what is the total number of comparisons that is required. Okay. So how do we measure? So the first thing is, for a fixed input B, the algorithm, so there is only one permutation, right? So remember that the algorithm is deterministic, it does not do anything else, it just looks at the input and compares. It might modify the input, yes, based on the comparison, nothing else it can do. Okay, but these are all deterministic, right? Once the input is fixed, everything is deterministic. So once the input is fixed, for a fixed input, your algorithm will be basically tracing a path in this tree. So it will reach here. Okay, so I'll write it down here. On a fixed input, the algorithm traces a unique path. In the tree. Outcome of the algorithm or output of the algorithm is the label of the corresponding leaf. Once you say unique path, I mean there is a unique leaf, right? Path only goes from root to leaf, it ends in leaf, otherwise the path still can continue. Okay, so algorithm stops only at the leaf. So at the leaf there is a permutation labeled. So output of the algorithm is exactly the permutation. I mean that is how we label the permutation. So we label the permutation based on the output. Okay, so that is how our algorithm works. Now what is the number of comparisons done in this path? It's basically the path length. So length of the path is the number of comparisons. So I'll move to the next page. So number of comparisons sorry performed is equal to the length of the path traced by the algorithm or path followed by the algorithm on the given input. Okay, so yeah, so let's say the height of the tree is h. Okay, so suppose h be the height of the tree for the algorithm. Okay. Then, since it's a binary tree, the comparison outcomes are only 2, right? For any comparison, the outcomes are only 2, so it's a binary tree. Then the total number of permutations represented in the tree that is potential outputs of the algorithm equal to 2 power h. Okay. Sorry. Okay. Yeah, so now we have some parameters here, right? So we have some information here. So total number of permutations represented in the tree is 2 power h. So total potential outputs of the algorithm. So if I vary the input, so as varying the input, you will get different permutations, right? So total number of permutations is 2 power the height. And what is the number of comparisons? So height of the tree is the number of comparisons. So now what is the worst case number of comparisons? Maximum height of the tree. Okay. See, once you fix the array size n, the comparison tree or this decision tree is fixed, right? Given algorithm, the decision tree is fixed. You know what is the decisions made. Okay. So once the decision tree is fixed, sorry, we know the set of all permutations being output. Okay. So, and we know a total number of permutations that can be output. So my claim is, if the algorithm to work correctly, so claim 1, for the algorithm to work correctly, total number of permutations output by the algorithm by the algorithm should be n factorial. Why is that? I'm sorry, some problem here. So I'll just give you a proof. So the proof is fairly simple. Okay. So suppose the number of permutations is less than n factorial. So proof by contradiction. Algorithm outputs less than n factorial permutations. Let sigma be a permutation that is not labeling any leaf of the tree. See, given any permutation, I can always construct an array such that the output permutation, that is the sorted element or the sorted array, corresponds to this permutation. Okay, so pause for a moment and convince yourself that this is possible. All you do is you just apply this permutation, the inverse of this permutation, you immediately get the array. That's it. You take the sorted array and apply the inverse permutation of it. Okay, so for any permutation you can construct an array. So let B be an array such that the sorted array of B corresponds to permutation sigma. Okay. Now what does your algorithm do with respect to sigma? So remember that sigma is not labeled by any of the leaves, but we know that it will trace some path, right? It will say trace some path, so the algorithm will trace some path, but you will find that the leaf is not labeled by sigma because sigma is not even occurring there, right? So your algorithm must be outputting incorrectly, right? Because for any array, the sorted sequence corresponds to a unique permutation. Okay, so that's again convince yourself that the permutation is unique. Okay, so you can take this example, the example that we have here, or you can, for any example, you can always, because the elements are distinct, right? The permutation has to be unique. If the elements are not distinct, the permutation will not be unique. Okay, so yeah, so now the algorithm will output something different. Output some different permutation, hence will not be sorted. Okay, so this is the contradiction. So there are two things which I have left without proving. One is the permutation is unique, which I hope you convince yourself, and the second, for any permutation you can come up with an array. Okay, yeah, I'm not proving it right away, you can always do that, it's fairly easy. You can just take the sorted array, consider the inverse permutation of the given permutation, that will be it. Okay, so yeah, so that's it. So if at all the algorithm misses on one permutation, I can construct an input where the sorted sequence corresponds to that permutation and run the algorithm on it. Be assured that the algorithm will output incorrectly because that permutation is not even represented in the tree, right? The algorithm output is one of the permutations which are labels of the leaves in the tree. Okay, so yeah, so that's it. So what do we do? Oh, what did we do? So the total number of permutations has to be n factorial. So therefore 2 power h is at least n factorial. Therefore h is at least log of n factorial. Okay. So this is approximately omega n log n. So just read this part to you, prove it. Maybe I'll discuss it in the tutorial. Okay. So yeah, so that completes our lower bound argument. So what we have proved is for any comparison based sorting algorithm, the number of comparisons must be at least n log n up to a constant factor. So omega n log n. Okay. So with that I'll end today's lecture. So next lecture we will be looking at, we'll be revisiting the quicksort algorithm and we will be studying a randomized version of quicksort algorithm. So like I had mentioned, today's lecture again is based on Bloom's notes. So Bloom's notes, I think third, or I think lecture number 5, but in the file I think third or fourth. Okay, so please check it out in the folder. Okay, so we end here.